Okay, so I'm going to change this question just a little bit. Instead of saying how many carbon atoms, I want to say how many grams? How many grams of carbon atoms are found in a 551.29 gram sample of copper 2 carbonate? So our goal is grams. Okay, we're really looking for grams of just carbon. Okay, so in the past, I taught you how to do this problem using a conversion, a mole conversion. But I'm going to show you an alternate way to do it. And the alternate method really works best when we start in grams and we're trying to end in grams. This is when this works best, because we're essentially going to find the percent composition of carbon. And if we know that this particular compound is 30% carbon, then I can just find out, well, what's 30% of that number, right? That's really what I'm going to do. The reason it's easiest when they're gram to gram is because our ratio is just the same, right? We're able to compare gram to gram really easily. So when we're starting grams and we're looking for grams, we can do a percent composition problem. But before we can even do percent composition, we need to know, well, what is copper 1 carbonate? What's the formula for copper 1 carbonate? So let's go ahead and get periodic table and periodic table of ions out and see if we can formulate what is the chemical formula for copper 1 carbonate. Have you found carbonate in the box, or do you remember what it was? CO3 minus 2. So my chemical formula here, after we do the crisscross, would be Cu2CO3. Do we agree with that? Cu2CO3. So copper 1 carbonate looks like that. So I want the percent composition of copper 1 carbonate, but I don't need to really break it down into all of the different elements, do I? I just need to know what percentage of this molecule is made up of carbon. So the first thing I need to do is find the molar mass of Cu2CO3. So copper's 63.5 or 63.6, wherever you want to round that, times 2 plus carbon plus 16 times 3, right? That's how we solve for molar mass. I got somewhere around 123.2 grams per mole. Tell me if that's what you got for your molar mass. Okay, yes, this is wrong. I forgot to multiply that by 2. So let's try it again. How about 186? 186.4. Okay, very good. I make mistakes too. Okay, very good. 186.4. So that's the molar mass. Now to find my percent of carbon, I take carbon's part of it divided by the total. Okay, and if I wanted a percent, I really am going to take it times 100, but I'm not going to write that out. So I'm going to take 12 divided by that. And I get somewhere 0.0643. And so what would that translate to in terms of percentage? How could I put that into a percentage? 6.4%. Right? I'm going to take that times 100. But for my problem that I'm doing right now, I actually don't even want to, I don't want it into a percentage. I actually want to keep it in the decimal. I want to keep it in the decimal, and here's why. Because if I want to find out, okay, let's talk through our problem here for a second. If I know that my compound is 6% carbon, 6.4% carbon, and I have a sample that is 551.29 grams. Don't I automatically know then 6.4% of this sample would be carbon? Agreed? So I just need to find out, well, what's 6.4% of 551.29? And so how do I do that? I take the percent that has been converted to a decimal and I multiply it by my total. So let's just keep the decimal that we have right here, and we'll take it times 551.29, and I get 35.5 grams. Oops. 35.5 grams of carbon. So these are two types of chemical formulas that we will study. Basically, kind of similar to the category of ionic and covalent formulas, but just a little bit different, okay? When we talk about these formulas, the first one we're going to talk about is called empirical formulas. And empirical formulas are the most reduced version of a chemical formula. The most reduced version of a chemical formula. That would mean that all ionic compounds are empirical formulas, right? All ionic compounds, all that we've studied here with ionic compounds, we always reduced those down, didn't we? So those would all be considered empirical formulas. They are the smallest ratio they could be. Okay, let me give you an example. If we had aluminum, which is +3, and phosphate, which is -3, we do not put that formula as Al3PO43, right? We reduce that down to be AlPO4. So ionic formulas are always going to be considered empirical formulas. But a molecular formula, on the other hand, is the exact chemical formula of an unknown, which means it could be the most reduced version, or it could be a covalent formula, a covalent compound that is non-reduced. So this might be C2O2 or P3N3, right? Those are examples of molecular formulas, and they are non-reduced. So a molecular formula, it could be, let me say this again. Typically when we're talking about these types of things, we're trying to identify an unknown formula. That's our goal. We're going to be given information about a compound, and we really have to build or identify what compound it is. And so when we're trying to find its molecular formula, it could be, it's the empirical formula of that compound. That could be the one that we're studying, or it could be the non-reduced version. So I'm going to show us how do we check that, how do we not, okay? So I'm going to give you kind of a set of steps here as to how to build the empirical formula. So I maybe didn't lay this out perfectly, but all of these steps listed right here actually allow us to solve for a compound's empirical formula, because that's the first step. We need to know what is the ratio of our elements. Okay, that's basically our empirical formula. Let me ask you this question. If I have C2O2, that is considered a molecular formula because it's non-reduced. What would the empirical formula of this compound be? The empirical formula. What would be the most reduced version of C2O2? CO, right? What if I had a molecular formula that was C3H6? What would the empirical formula of that compound be? CH2, right? Do we see how we reduce that down? So this would be the empirical formula, and this is one version of a molecular formula. Okay, if I have the empirical formula CH2, that means I could have C2H4, C3H6, C4H8, C5H10, right? Look at all of the list of molecular formulas I could have. It's any version that has the same ratio, okay? But the thing is that all of these compounds, because they're covalent, they all behave differently. They have the same ratio, but they behave differently. They have different characteristics, different properties. Because they are covalent, the way they fit together is totally different. In ionic compounds, every NaCl behaves the same, right? Because it always gets reduced down to be NaCl, right? That's how it fits together. No negotiating, right? That's how it goes. So in covalence, we have a little more flexibility there. But let's go ahead and start looking at our list kind of rules here of empirical formulas. Typically, when we start with a question like this, we're given a percent composition to start. We're typically given a problem that says, I have a compound with this percent composition. It's 30% carbon and 20% hydrogen, and it gives us the percent composition. And our goal is basically to undo the percent composition and build it back to its chemical formula, right? Figure out what is our actual formula. So what we're going to do is just move our percentage straight into grams. So if it says 30% carbon, we're just going to relabel it as 30 grams of carbon. And we're just going to assume that this sample we're working with is 100 grams. So our percentage is split up exactly like that, right? We get to just look at ratios here. So we're taking our percentage and just switching it into grams. We will convert all of our grams to moles. Okay, so take each of our grams and convert them to moles. Our next step is divide each one by the smallest number of moles. That allows us to see the true ratios of how many atoms of each element we need. And then we use our ratio to build our formula. So these rules and these steps seem kind of arbitrary, but let's just go ahead and dive into a problem here. Okay. Do you guys have this slide printed for you? I have a handout here of some extra problems, but do we have these ones printed? Okay. So let's go ahead and try one here. It says, an unknown compound is found to have a percent composition as follows: 32.38% sodium, 22.65% sulfur, and 44.9% oxygen. What is the empirical formula of the compound? So when we're solving for empirical formula, that means we're trying to get ourselves to build the most reduced version of how all of these elements need to go together. Okay, based on the percent composition. So we're going to write each of them out, and we're going to just switch the percentage to grams, right? We're going to relabel them. So the way I lay them out is like this: 32.38 grams of sodium, and I know I'm going to convert to moles, so I just go ahead and give myself some room to do that. 22.65 grams of sodium. Oh, not sodium, I'm sorry. Sulfur, S, and I'm going to convert that later. And then 44.99 grams of oxygen, and I know I'm going to convert that later. So I line them all up just like that, and I label them with grams, knowing I'm going to convert them to moles in just a minute, right? Because that's really step 2, if you want to label it like that, right? We started with percent composition. That's not really a step. We labeled them with grams. We're going to convert each to moles. So if we look at our first one here, grams of sodium to moles of sodium, we need the molar mass. 1 mole of sodium is 23 grams. And for this conversion right here, this converting to moles, I'm going to really suggest that you keep several decimal places. Because when we look at ratios in the next step, we want them to be as exact as we can. So I want you to keep a few decimal places when we convert to moles. So 32.38 divided by 23, 1.408 moles of Na. That's what I want. I want you to keep a few decimals there. Okay. We're going to do the same thing for sulfur. Grams of sulfur to moles of sulfur. 1 mole is 32 grams. We know where I'm getting this number 32. Where's that coming from? Atomic mass or molar mass, periodic table, right? It's coming right from the periodic table. So 22.65 divided by 32 gives me about 0.708 moles of sulfur. Are we on the same page so far? Everybody hanging in there? Mm-hmm. Okay, the last one is going to be converting grams of oxygen to moles of oxygen. 1 mole is equal to 16 grams. That gives me about 2.812 moles of oxygen. Okay, so if you look back at your steps, we've switched percentage to grams. We've converted grams to moles. And so now what we're going to do is take the smallest number of moles that we have and divide every one of them by that number. So which of the elements is our smallest number of moles? Sulfur. So I need to divide all of them by sulfur's moles. So that means I'm always going to divide something by itself, right? So I take this divided by 0.708, and that tells me that I need one sulfur atom. Okay, I'm going to come do the same thing up here, divided by 0.708. Oops. That gives me 1.988. That's really, really close to what?
2.
It's really close to 2. We want to go ahead and take that to a 2. Okay, in this step of dividing by the smallest number of moles, this should give us a nice pretty ratio, like a nice maybe usually a whole number ratio. Okay, and so I'm also going to do it down here on the bottom, 0.708. This gives me 3.97, so what am I going to round that to? So I need 4 oxygen atoms. And so the way I now build my formula is I come and say I need 2 sodiums, Na2. I need 1 sulfur atom, and I need 4 oxygen atoms. We built the formula Na2SO4, okay, sodium sulfate. Okay, so this unknown compound that we started with ends up being sodium sulfate. Okay, tell me what questions we had. Yeah, go ahead, Peter. So if we get a number right here that does not come out to be a nice, pretty whole number, then we've got a couple options. If we get, and we're going to look at those options here in just a minute, but if we get something that comes out at like 2.5, we're going to have a solution for that. So I'll walk you through that in the next one. But if I get something that's like, 3.88 or, 2.24 or something like that might be a clue that something earlier went wrong. One of my molar masses was wrong or something like that. Or, typically it's going to come out either very close to a whole number or very close to a half. Those are kind of our options. If they don't, then maybe we're going to go back and look and make sure we didn't make a mistake somewhere earlier. Okay, but I'm going to show you what the solution is when something comes out at a half like that. Okay, we're going to look through one of those. Okay, let's try this one right here. 26.56% potassium, 35.41% chromium, and the remainder is oxygen. How would we find the remaining percentage there? And what? Subtract it from 100, right? So we'll go 26.56 grams of potassium. Remember, we're going to put it right into grams. .41 grams of chromium. And the rest is oxygen. So we're going to take 100% and subtract out 26.56 and 35.41. And so I get somewhere around 38.03 grams of oxygen. Did we feel okay about those? How we do that? Okay. And so now we're going to just move through the rest of our problem. We're going to convert grams to moles. Chromium, let's call it 52. Okay, so for potassium, I got about 0.681 moles of potassium. And I got about 0.681 moles of chromium. What do we get for oxygen here? 2.37 moles of oxygen. Okay, now remember, this is not the point where it's supposed to come out to this nice, pretty whole number, right? This is just when we're converting to moles, so we don't need to be worried about anything yet. What's the next step here? What's our next step? Divide by what? The smallest number. Okay, so these are pretty much the same, aren't they? And when I divide by themselves, I'm going to get 1. So I know I'm going to have 1 potassium, 1 chromate. So now when I take this divided by 0.681, I'm going to get did I get a nice whole number? I got 3.49. So that's really not close enough for me to round and assume the ratio is 3. And so here's what the solution has to be. Okay, if I was going to build the compound like I have it, it would be this. KCrO 3.5. Can I do that? No. It doesn't work, right? And I don't think it's close enough for us to just say, oh, we need 4 oxygens, or oh, we need 3 oxygens. That's really not the case. The ratio is 1 chromium for every 3.5 oxygens. So what has to happen is I have to multiply my whole thing times 2 to get it to a whole number. So now my formula becomes K2Cr2O7. Right. When I have a ratio that comes out to be a 0.5, I have to double that whole entire formula to keep my ratio intact, but also get myself to a whole number. Okay, so does that answer your question, Peter, about what happened? Yep, that's perfect. That's what we want to do. Okay, we have to keep our ratio intact, but we also have to have compounds that have whole number ratios. Okay, so that's what it needs to be. Okay, let's go ahead and try this last one together here, and then we'll move into molecular formulas. Okay. This question says, let me make it a little bit bigger here, sorry. Analysis of a 20-gram compound containing only calcium and bromine indicates that 4 grams of calcium are present. What is the empirical formula of the compound? So let me ask you this question. Is there a reason for us to convert our grams to percentages to go back to grams? There's not, right? We're already starting in grams, right? They gave us a little bonus here. So we're just going to keep it, right? It says 4 grams of which one? Calcium, Ca. And so how many grams of bromine must I have? How many grams of bromine should I have then? It says the total sample is 20 grams, and it has only calcium and bromine. It should be 16. So 16 grams of bromine. Okay, so we're going to convert them from grams to moles. Bromine We can take that to 80 if we want to. So we've got our moles calculated here. I know I'm going to take it divided by the smallest, which means I'll need 1 calcium. And I would need 2 bromines, which becomes CaBr2. And isn't that the exact ionic formula for calcium bromide? Right? We know automatically that an ionic compound is going to be its empirical formulas. So if I knew this was calcium and bromine, I probably could have taken a pretty good guess that my formula was going to be CaBr2. Right? I probably could have taken a pretty good guess on that. We said empirical formulas are the most reduced versions of their compound, but molecular formulas are not necessarily so. Okay, they could be a reduced version or they could be a larger covalent compound, right? Remember, you'll never have a larger non-reduced version of ionics because that's the definition of an ionic compound, is that it reduces. So I'm going to show you kind of how we get there, okay? This says determine the molecular formula, that's the molecular formula, of some unknown compound. We know it has an empirical formula of CH, and we know our unknown compound has a molar mass of 78.11 grams per mole. So we know that our unknown compound is some version of CH. It's either CH or C2H2 or C3H3 or C4H4. You know what I'm saying? It's one of these versions, some version of that, but we don't know which one it is. So the way that we start to check that is to find out, is my molecular formula, how much bigger than my empirical formula is my molecular formula? So the first thing I need to do is find the molar mass of the empirical formula. Find the molar mass of the empirical formula, which would be 12 plus 1, so 13 grams per mole. Is my unknown just going to be CH? Does this molar mass match the molar mass of my empirical formula? Does it match? No. So that means my unknown compound that I'm trying to study, it's not the same as CH, right? It's the same ratio, but it's not CH. It's C2H2 or C3H3 or C4. It's one of those bigger ones. So the way that I find out how much bigger it is I take my unknown compound molar mass, 78.11, divided by my empirical formula, molar mass, 13. This number, like, absolutely should come out at a whole number, okay? Like, very close to a whole number. 78.11 divided by 13 gives me 6.00846 something. So it's telling me that my unknown compound, which has a mass of 78, is 6 times larger than CH. Right? This is what it's telling me. It's 6 times larger than CH. And so then what I come over and do is I just basically take CH, right, and I multiply my 6 through it, and I get C6H6. And that's it. So this unknown compound that we were trying to study that had a mass of 78, its formula was C6H6. Okay? We're going to always take, when in doubt, if you can't remember which one goes on top, take the bigger number divided by the smaller number, because that ratio can't come out smaller than 1, right? It's either the empirical formula or it's bigger than that. It can't be smaller than the empirical formula, right? Because the empirical formula is the smallest version of it. So always going to take our unknown molar mass divided by the empirical formula molar mass. And we get some ratio that we then distribute through the empirical formula. Okay. If 4.04 grams of nitrogen combine with this many grams of oxygen to produce a compound with some molar mass 108, what is the molecular formula of our compound? So we're given just some basic information here. Our goal is to find molecular formula. But did they give us the empirical formula in this problem?
No.
They didn't. So that means we have to solve for it first. So we have to do all of the mole stuff, all that. We have to do all that stuff first before we can even get to talking about the molecular formula. So lucky for us, this one started us in grams. So we're able to just start right there. We don't have to do anything with percent composition. So let's take 4.04 grams of nitrogen. We want to take it to moles. And we're going to do the same with oxygen. So for nitrogen, I had it at about I had about 0.2886 moles. And for oxygen, I had 7125 moles. Does that look about what you had? Or no?
Yeah.
Yeah, close enough, right? I'm keeping a couple decimals, but are we somewhere in that range? Oh, 11.46. I only accidentally plugged in 11.4. Okay, so we're slightly different there, but not too far off.
Yeah.
Okay, so we're going to take this divided by 0.2886, and we get about 2.5. So 1 nitrogen to 2.5 oxygens. So that's not going to work, right? It's going to be NO 2.5, right? That's not going to work. What should we do here? We're going to multiply that by 2. So that becomes N2O3. Now, is this the molecular formula? Is it the molecular formula?
No.
It's not, right? This right here is the empirical formula. So now, in order to find the molecular formula, I'm going to come up here and say, my unknown has a molar mass of 108. Sorry, go ahead.
Supposed to be N2O5.
Oh, you're right. Thank you. Yes, you're exactly right. N2O5. Yep, exactly. Thank you. N2O5. Thank you. So I need to find let's find out, what does this one weigh, right? What does my empirical formula have a mass of? So 14 times 2 plus 16 times 5. This gives me 108 grams per mole. So what's the case here? It matches the molar mass of my unknown thing, which means that my empirical formula was N2O5, but my molecular formula was also N2O5. It just so happened to be that the compound I was studying here was the empirical formula as well. Okay, so in this case, our molar masses matched, which means I knew that the one I was studying up here was also the empirical formula. So they can be the same, right? If that just coincidentally works like that.